Hi, this is the second of our kind of round table chat about model making, 3D printing, laser cutting, CNC, etc. So we started this week's one off by just comparing the STL files for this model. This is the Solverein Solverein Business School. That was its original name. In Essen in Germany, and by Japanese architecture firm called Sanaa, Sanaa. Really kind of pretty cool, cutting edge duo of architects. Do some really interesting buildings. But this is going to be pretty obvious what happens here. This form is going to require a lot of scaffolding because there's a big roof and nothing else inside. This form requires a fair bit of scaffolding, notably in all the window openings, because they're just a little too big to bridge across. The 3D printer can't just throw a line across these. But then if you tilt the whole model at 45 degrees, it eliminates the scaffolding, providing you put in some support, because it's inherently kind of likely to fall over because it's heavier on this side because of the roof as well. There's no roof on this side. So what I'll do is just export these as STLs, and then we'll take each one into create the slicer software, and you can see the difference in the way they're set up. So I'll just pop these on the desktop, and I'll just call this normal. Okay, we'll send this one out, and we'll call this one rotated. We'll call this upside down. Be easier, upside down. And then we'll send this one out with all its legs and little base details, and we'll call this one 45. So 45 degrees, and it's upturned. Okay, so let's have a wee look in the slicer. Unload each one and just have a look at the time impact that has. So this one is normal. Okay, it has to do a lot of scaffolding on this, so it takes a long time to work it out. Okay, and let's have a look at the layers as it's doing that. So you can see it's basically filling the whole center of the model with scaffolding, as well as the window openings. And that's a massive time hit. 48 hours, 44 minutes, 2 days. If all goes well, it's 2 days. Okay, the scaffolding is quite flimsy, and it has a chance of failing. You're using about 1/4 of a spool of material, so that's at least 5-6 pounds of material as well. So let's clear the platform and go back to normal, and we'll load in the upside down one. Upside down. Okay, let's have a look at this in layers, see what's happening here. And you can see all it's doing now is just filling in the windows instead. So it should be considerably quicker because it's not having to deal with the center. Yeah, 21 hours, 26 minutes. So it's still pretty much. There's a quality issue with all this infill and all this scaffolding. Are you going to be able to clean out all those windows and get all the scaffolding out? Sometimes it sticks pretty badly, other times it pops out really easily. It's difficult to tell what's going to happen. So 21 hours, 26 minutes for that one. Let's clear the platform and load the last version, which was called 45. Okay, let's have a wee look at the support situation here. Okay, I'm not seeing any scaffolding at all. Okay, it hasn't quite finished its calculation yet, so I've just got to leave it a few more seconds to see the full calculation. Okay, what I'm going to do is get in a bit closer and have a look at an area and see what happens with the layers. Okay, so it's still quite a long time. It's a bit longer than the previous one. Okay, but there isn't any scaffolding to deal with afterwards. Okay, so let's take this down a bit to say about here, see what happens. Okay, so on this side things are quite easy because it's just, you know, running around the top, and as we go up another level it does a bit more. But on these ones it's got to actually jump across, so it is having to kind of bridge across these gaps. So it's being fairly brave, and it's kind of jumping. You can see it just here. You can see what's happening here. It's taking some strands across. It's doing some bridging. Okay, and that's another. In that way, it can avoid doing the infill. So we're seeing quite a lot of blue lines appearing in the window openings there. So those are kind of a line kind of thrown across to help it start creating the kind of the window heads, the lintels. Okay, and that's called bridging. And if it's not too far and, you know, it thinks it can do it, it will have a go. But if the gap's a bit too big, it kind of chickens out and has to put in some scaffolding. Okay, so we'll go to the table now and look at this with the other first year models. This is one of the examples that I'm using with the first years, you know, a simple cubic building, showing them kind of taking elevations and applying them to a cube and then cutting out holes. So it's a pretty simple kind of modeling exercise, but they do have to be kind of fairly rigorous and make sure they get their things in the right side and the right face of the building. So it's good practice using the UCSs for the obvious ones, you know, left, right, front, back, etc.
We're kind of looking at, you know, very simple geometries, but, you know, if you can get this stuff right, then the more complicated stuff isn't so complicated. So that's the wee kind of Luxor hotel in Las Vegas. So it's, you know, from the outside it's very plain, but on the inside it's got these kind of lift shafts that go diagonal. Very clever. Okay, anybody recognise that? No? No? One of the biggest buildings in Europe? You don't recognise it? La Défense in Paris? Oh my god. It's the biggest cubic building on the planet. It's like, this is the kind of main axis of Paris, and the Eiffel Tower's here, and this is at the other end of it. It's like quite a big landmark. Have a look at it. Amazing structure. So that's La Défense. So these are all kind of different. They're all the wrong scale. They're not the same scale, obviously. Somebody will recognise this one, because this is where I first saw the building. I was like, hold on.
Have you not seen it before?
I haven't seen it before.
I've been in there.
It's brilliant.
They have one. Well, they used to have one of them that is like an exhibition.
Yeah.
Is it the ones in Rotterdam?
Yeah, the wee cube houses. Yeah, but
And they have
it's
the
much
pencil
bigger.
next to it as well.
It's a much bigger kind of complex. There's loads of these, but the trick with this bit of CAD work, I'll use the word, is how do you get the cubes overlapping? Because they're not just touching each other. They're not built just next to each other. They overlap each other by the thickness of the wall. So that's actually really tricky to set up. But that's what I want them to get to, is kind of be able to kind of do that control, be able to kind of turn the coordinate system, you know, and have that kind of confidence to know what they're doing with the coordinate system. Because that in AutoCAD and Rhino, you know, pretty much the same piece of software basically. If you start with Rhino, you can use AutoCAD. If you start with AutoCAD, you can use Rhino. It's no problem. But they both have this construction planes set up in them, and you know, that's the key to kind of being able to model properly, is be able to orientate your coordinates correctly. So, you know, that building was one of that kind of set, and I was like, can we kind of go with that? So I was like, I want to do it with White. I had this. It's called ePLA. It's supposed to be engineering PLA, but I don't know if I've just got a dodgy batch of the stuff, or it's just crap. every model is a real nightmare, and it's just not sticky enough. It's like there's not enough plastic in it. It is a matte kind of material, which looks kind of nice and kind of milky, but just not sticky enough. And when you go to when you get a spool out that's kind of shiny, everything's easy. Because it's a much higher plastic kind of content. So this is the one that kind of failed. You can see it's kind of just sneaked up at the end there and kind of spoilt it. So finally got one to actually print properly. But as you can see, these bits are breaking off, so you wouldn't tidy those up. But there is, a bit of what we kind of call stringing going on. It's a bit shabby inside, so a bit of tidying up. And one thing I didn't notice until it's finished is there's a kind of a change in the way the print is behaving about halfway up. And the only thing I can think of is that it was kind of during the day up to then, and then it went into night time. So the temperature in the room gets colder, and it does affect the behavior of the print. You have to watch out that the machine's not in a draft or something like that, because it really does not like that. So this is the wee explanation of the bridging. So I'll kind of get these visible more better in the video, but it's kind of showing a wall vertical and showing a wall that's leaning like this. It's at 45 degrees. And so generally, when it's creating anything, it does perimeter first. It usually starts with these. Usually there's kind of three runs around an object. So it starts with this one. So it goes round, comes back there, then it goes round again, comes back to that, goes round, does the outside one last, and then it comes back and fills in between, in the middle. Sometimes it's just straight lines. If it's a very narrow wall, it'll just kind of zigzag and do it kind of quite quickly. So that's what that is, implying just the infill. Okay, but on a vertical wall that's got a reasonable amount of thickness, then it cannot do the bridging. It cannot just take a line across like it's throwing a rope across. So that's where the scaffolding comes in. So it has to build up this scaffolding so it can eventually lay these main lines across at the top. But on the angled one, it kind of gets away with it because it's only kind of running one. Because it's only running that very first one. It says, okay, I'll give it a go. So it kind of chucks one line across, and then when it comes round, it will do that one. So it will make that one a little bit stronger because it's gluing onto the top of it, and then it does them on either side, and it starts to to widen and get stronger as it goes up. So sometimes it kind of depends on the thickness and the weight of the model as well. So this was kind of dismaying, the amount of time it was going to take, 23.5 hours. It's like, what? No. If you wanted two of those, oh God, that's pretty heavy going. So I thought, right, we've got the drawings, we've got the CAD files. Let's see what a laser cutter could do instead. So I've got the kind of 1 to 250 version here. Okay, and in time wise, there's about half an hour of working out how the thing's going to connect. So these notches have to kind of come into the equation. You could just join things edge to edge. That's no problem. But notching is quite good fun. It does look quite cool. So it's kind of worth doing, and it gives it a more definite kind of connection. This isn't going to stand up without tape. It will just kind of keep falling over. Okay. But like we saw last week with the joining 3D printed ones together, you've also got to allow a little bit of space for this to go together. Otherwise, it can be too tight. You get stuff stuck, and then you pull it and you snap it. It's so easy to snap MDF. It's not got much strength really, and it's as thin as this. So what I generally tend to do is set the shape out and then an offset of just 0.2 millimeters. Okay, so every one of these is 0.2 millimeters bigger than the bit that's going into it. So it fits just right. Okay, but that takes a bit of working out, and you've got to kind of keep your wits about you. I've actually messed this up. When I went to 3D print it, it was like, I've done something wrong here. It's not until you kind of get there, is it? So this is actually about, it's one thickness of the wood smaller than it should be. So I have to do a quick rethink and inset the lid instead of the lid. The lid was supposed to be kind of on top and cover these joints, but quick change of plan. Had to get it cut on Friday, or I wasn't going to be here today. So these things happen. You kind of can get away with it, or is it like, oh, got to reprint these as well? But time-wise, it's completely different. It's 5 minutes cutting on the more powerful laser. That's 3.2 millimeter MDF, and similarly, this was only about 15 minutes cutting, if that. Most time, it took more time to pick up the little squares than it did to cut the damn thing. Can't get them off the bed. But I've kept all the little squares. I'm not going to waste them. I'm going to make a little Minecraft world at some point. I've got a big bag of little squares. So useful actually, for strengthening. If you're making this and you were going to glue it together, all these bits make good little kind of corner stiffeners and things, because they're absolutely lovely square corners, rather than going and making another load of them intentionally.
Then I can look at the burnt look.
You sand it. You can just sand it, lightly sand it.
So that isn't.
Well, you can't stop it doing it,
Yeah,
but you can
yeah.
you can paint it as well. So if I want it to look like concrete, it doesn't at the moment. It looks like it's in Zaporizhia or something. But I would just get some paint, just some emulsion paint. Might take 2 or 3 coats because it kind of soaks in really quickly. But inside, it really is a bit of a bomb site. Inside, it's all yucky. And another downside of laser cutting is it smells as well. The models tend to smell a bit, unless they're expensive materials like acrylic, where they're a bit nicer, but hugely expensive in comparison to MDF. So this is a really useful tool to use as well, because when you look at a catalogue or whatever, that's 6 millimeter MDF, but it's not. It's 6.1 millimeters, and that's advertised as 3 millimeter MDF, but it's not. It's 3.2 millimeters. So we've got the accuracy in the CAD, and you kind of have to allow for that, because otherwise it could be way too tight once you try and put it together. So really useful little device. You just put it on, and I just usually kind of squeeze it. So that one's saying 3.3. Might be slightly different further along. 3.6 there. 3.3. 3.2 flashed up there. 3.2 is kind of varying all around. So that's your kind of your thickness one. But at the back of it, it's really useful. This is for measuring holes. So if we have a gap that we need to find the width of, you use the back of it instead. So extremely useful little gadget. These are dead cheap now. You get them on Amazon for $5 or something. So you kind of go a bit crazy. Kind of go around checking things. I was measuring this earlier on, and it varies ridiculously. And there's things swell. Once they're kind of put in place, they can expand. They can. It depends how well they're kind of joined together. Okay, so scale, kind of staying with the scale kind of thing. I think I've covered all the points there. Got some stuff here that's looking at scale, and quite fortuitously, this got broken on the way here. So it was a little kind of tensile structure model. This is from Grasshopper. There's a feature in the software called Kangaroo, and it lets you generate nets and tensile structures. You tell it where it's going to be fixed down, and you tell it how much force you want to apply on it. So this is kind of an upwards force, and you tell it how elastic you want the components to be, and it goes wah, 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 wah. It doesn't make noise, but it does the animation. It's like it's made out of kind of jelly, and it stabilizes at the correct position. So you can change the forces, and it'll bring it down, or let it more relaxed. It will go up. So it's trying to see how our 3D printer could manage it, straight off, just sending it straight to it. this has been kicking around for about a year and a half, so I'm not sure if it's just dried out. It might have dried out a bit much as well. PLA, the printing material, is quite sensitive to moisture. It can go brittle very quickly, so you have to kind of keep it in bags or in Tupperware containers to stop it going off. But that kind of snapped, and so the issue there is that it's very small. All the parts of it are very thin and delicate, so it's likely to get damaged. So this is a portion of that at a much larger scale, so 5 times the size. But it would be too big for the 3D printer. It's going to be enormous. You could try and kind of join it together. So it was actually printed kind of that way up. That's the way it's printed. So that's another kind of issue with scale, is the kind of fragility of the model. You're getting so small that the bits between windows get zapped. With laser cutting, especially, if you try to do something too fine, you can end up the laser goes too close to the previous one, and it just vaporizes the material. It's gone. So you're left with there's supposed to be lots of like a barrier here, or window mullions, and they're all gone. It's like, too small. So you sometimes have to kind of exaggerate things to get them made. But that's all part of models. It's not necessarily perfection. You go and look at the thing if you want to see the real thing. It's a model of it. So this is something we're looking at with first years this afternoon. I'm going to get them to draw up a little survey of sea brays. And I thought, I've got the model, so let's print it out. So this is a 1 to 5,000 model of sea brays. Simplified so that it could be turned into solids.
Okay, I'm just going to jump in here so you can see in a bit more detail, because the model I'm holding in my hand is very small. So this is a highly simplified version of a 1-to-1 model that we produced a few years ago for second year's site location. So if I just go to that model, you see here it's basically kind of a single 3D face thick, which is all you need for visualization. There are some solids here, like the low wall and the gate posts, the hedge, the steps here, and then a lot of detail on the handrails, so that this looked really good when visualized. That was the idea. But this is pretty much impossible to print. The only things that would show up would be the solids that I'd identified. There'd be a lot of work in trying to turn this into a solid object. So what we did instead is just kind of simplify this, and if I shade it, you'll get the idea. It's much cruder because it's going to be tiny. So I 3D printed the hedges as separate objects. I can get it to select. That's better. So these are separate objects, and the little copy bandstand was a separate object as well. But everything else was basically printed at the same time because it was fairly simple. Okay, and what I did here as well was dip the path very slightly so that I could paint the green area. So I could paint the grass area here. It just gave me a line. If I just made it slightly recessed to give me a line that I could then paint around with the acrylic paints that I'll talk about in a moment. Okay, just so you can get a better view of the model.
Perth Road actually kind of slopes this way a wee bit, but this is flat because you wouldn't be able to tell the slope on the road. It's so small. This has had a bit of a problem. It's a bit bouncy. When it first came off the printer, it was the other way around. It was like that. But you can use a hairdryer on 3D prints, and if you just hold it long enough, eventually they go soft, and you can kind of bend them. So it kind of corrects things. But I bent this a bit too much the other way. I kind of left it sitting between a couple of cups and with a weight on it, and it kind of bent it a bit too much. But this is kind of comparing the scale. This is a 1 to 10. This is 1 to 10 of the gate post there. So it's kind of. Well, this one's in 3 bits. Doesn't look like it, but good old blue tack. So that was the first print, because everything's kind of going inwards like a tower. Okay, so there's no overhangs on that. Blue tack's pretty good. This bit, because of the overhang, and I didn't want any kind of scraping, printed the other way around. Okay, the first attempt at that didn't print very well. It's not very flat. Kind of rocks, and so you can definitely see there's a problem in that one. And then the final bit, this wee pyramid, printed the right way up. So that's the kind of thing you've got to do. Kind of, you know, how do I split the object so I get the best quality? You know, you could have sliced it this way and glued two together. That would have worked. It would have been equally good. Yeah, it would have been. But you'd end up with a big join right the way through the middle of the object. So just went for 3 parts instead. And it took quite a long time to print, actually. It's quite nice colour though. Nice kind of sandy beige. None of that left. There was just a bit that I got chucked out from the Make Lab. Just enough to make that and no more. Okay, so that's kind of just a few kind of issues relating to scale. I thought to kind of put those on the table.
We'll just wind this off with just showing you how I would split this object up. So you don't want to lose your original one, so we copy it first. Okay, so we'll just copy it to the side, and then I'd look at the front view. Let's have a look at that plan. So this is the one that we'll chop up. Zoom out a little bit, and don't want to do anything in a shaded view. It can behave quite strangely. So we're looking to take this portion out so that we can print it separately, because we want this bit to be upside down, because it's when it gets to here there's going to be needing some support, and that support could go a long way down depending on how far out this was hanging. Okay, so what I'll do there is just draw a polyline out from here. Okay, and a polyline out from here, so that I can put a rectangle in that area. So I'll just put a rectangle there. Okay, and then look at that in 3D. I'll pull this towards me. I've got ortho on, so I'm just pulling that box towards me. Let's just get rid of those two, and then extrude that back the way. Okay, as long as it goes right the way through the object. Okay, now if we just extract this bit in the middle, we'll lose the other two. We'll lose those, but we need 3 pieces in the end. So what I'll do is copy this just now. Copy it again. Okay, so we'll do an intersection on both of these. So no, it'd be a subtraction on this one, but an intersection on this one. Okay, so subtract. Oh, let's just make this the current layer, so we keep the layer color. Try that again. Make current. Oh, it's a block. Is it a block? It is. Aha! I copied and pasted it in, so I wouldn't get anything subtracting. I wondered why I wasn't changing layer there. Okay, so subtract from this one, take away this. Okay, but on this one it would be an intersection instead. So it's the one that you don't use so often. Intersect of this and this. So you make sure you pick the right one first. Okay. Trouble with this one is that they're both still joined together, and that's where the solid separate command comes in. So you click it, press enter again, it should now be in 3 pieces. It should have 3 pieces. So these can be sent to the slicer. You could rotate that here, or you could rotate it in the slicer. Now, watch out when you send things if you're not in the world coordinate system, because it remembers that, and things can be the wrong way round when they arrive at the slicer. So you want to be into the world, and then you send these out as separate STL files. And that's how the column was broken up into 3 pieces. Okay, so to rotate that, you'd be in the front UCS, and then just rotate, find a midpoint there, 180, and then you're going to get a much better print quality.